Ok, stiamo registrando. Va bene, a questo punto dovreste vedere lo schermo.
Sì, lo vediamo.
Benissimo, allora cominciamo. Innanzitutto ho messo questa slide che vi ho già mostrato ieri per dirvi che c'era un errore qui. Quindi diciamo la combinazione di quark e antiquark nella slide che vi ho mostrato ieri, che ho anche caricato l'altro ieri sera sul web, c'era un errore, quindi diciamo adesso ho caricato quella giusta, quindi scaricatevi eventualmente se non l'avete già fatto, insomma le slide che trovate adesso sono quelle con la combinazione corretta di colori qui. Tra l'altro è proprio quella che ci servirà oggi, quindi. Ok. So let's start. So let's start with heavy meson and the QCD potential. So here you recognize the spectrum of the charmonium on the left and of the bothonium on the right, where charmonium and bothonium, as you know, are bound state of C anti-C quark and B anti-B quarks. Okay, and here you see all essentially the lowest energy states with the corresponding quantum numbers. We recognize here the J psi, for instance, for the charmonium and all its excited states, and the upsilon states. Okay. Now, different from the up, down, and strange quarks in the light mesons, the velocities of the heavy quarks in the charmonium and bothonium states are relatively low. So they are heavy, so they move slower. And in particular, the beta of the C quarks is of the order of 0.3. Okay, so only 30% of the speed of light, and the speed of the beta of the bottom quarks, which are even heavier, is just 10% of the speed of light. And then, as a consequence, the observed spectra of charmonium and especially bothonium states are well described by a QCD potential in the non-relativistic approximation. This is what we call the NR-QCD, non-relativistic QCD. We have already introduced this potential. Let's now derive it more formally. So in non-relativistic QCD, the quark-quark or quark-antiquark interaction are expressed by a static potential. Now, due to the gluon self-interaction that we have been studying yesterday, the potential at large distances is proportional to the quark separation. And this we've also seen yesterday, and it is essentially the reason for confinement. The more the quark pair or the quark-antiquark pair are separated each other, the higher this potential becomes, okay? And so you need an infinite energy to break the pair, essentially to create free quarks. But this is essentially the behavior of the potential at large distances. What now happens at small distances, okay? Now, in the short distance component of the non-relativistic QCD potential can be obtained by considering the analogy with the non-relativistic limit of QED, that is the Coulomb potential, okay, that you see here, the standard Coulomb potential. In particular, you know, this potential can be attractive in case of opposite charges and repulsive, so with a plus in case of same charges. So we can now apply a complete analogy, okay, with the Coulomb potential in the case of a short distance non-relativistic QCD potential. And this is how the potential would look like, okay, by considering the proper color factors, those that we studied yesterday. So we have a repulsive potential in case of quark-quark and an attractive potential in case of quark-antiquark. And then the distance dependence is exactly the same, okay? It is inverse of the distance, and on the top here we have, of course, the strong coupling constant instead of the electromagnetic coupling constant. So now we can make use of the totally symmetric color wave function of the mesons, the one that we discussed yesterday, to calculate the expectation value of the non-relativistic QCD potential for heavy mesons. Okay, so let's now move here. So this is page 1. Okay, so let me start with the color singlet wave function for a meson, so a QQ bar. I put a C to indicate this is the color component only. So this is 1 of square root of 3, and then we have red, anti-red, plus green, anti-green, plus blue, anti-blue. Okay. So now we can calculate the expectation value for the non-relativistic potential, and we can indicate in this way VQQ bar average. And this is nothing else than psi c, the potential VQCD, and psi c again. So now we can substitute the expression of the wave function here. So we have an overall 1/3 factor outside, and then we have red anti-red plus green anti-green plus blue anti-blue, our potential, and then red anti-red plus green anti-green plus blue anti-blue. And now we can take all the cross products, okay? So we're gonna have 1/3, and then we have, of course, 3 by 3, 9 terms, okay? 9 matrix elements. So the first one will be red anti-red, VQCD, red anti-red. The second will be red anti-red, VQCD, and then green anti-green, etc. And the last one would be blue anti-blue, VQCD, blue anti-blue. Okay. So in total, we have 9 combinations, or 9 terms. Okay. Now we calculate the expectation value for each of these color combinations. So for the first one, we have red anti-red, VQCD, red anti-red. And since it is a quark anti-quark pair, it is an attractive potential, so we have the minus sign. Then we have the proper color factor, which is the one red anti-red into red anti-red. And then we have, in analogy with the Coulomb potential, alpha S divided by R. Okay. Then for the second term, we would have red anti-red, VQCD, green anti-green, and this would be minus C, red anti-red into green anti-green, and then again alpha S R, etc. And the same for all other terms, okay? So now we can put everything together, and we extract our expectation value for the QQ bar non-relativistic potential. We put the alpha strong divided by R outside, so this is minus alpha strong divided by 3R, and then we just have to sum up all the color factors. So C, red anti-red into red anti-red, plus C, red anti-red into green anti-green, plus etc. Okay. So essentially here we have in total nine combinations, but 3 are corresponding to the first category that we have seen yesterday, and 6 corresponding to the third category. Okay. In particular, so this is for an example of third category for quark anti-quark. This is an example of first category. For first category are the pure, let's say, combinations. Okay. Let's say the diagonal terms, and the third category in this case corresponds to the remaining 6 non-diagonal terms. And so we know which values to put here, okay, because this we studied yesterday. So this is minus alpha S divided by 3R, and so we have 3 times the color factor for the first category, which was 1/3, plus 6 times the color factor for the third category, which was 1/2, if you remember. So this is 3 plus 3. So overall, this is gonna be now this is 1 plus 3 is 4. So it's minus 4/3 alpha S divided by R. And so this is, let me recall you, for the short distance. Okay, we can write everywhere short. Okay, so now we can combine all together with the long distance component. So overall, we can see that the VQQ bar R, which is essentially the V for the non-relativistic QCD as a function of R, is given by the sum of these 2 terms. The one that we just derived, which is the Coulomb-like term, which dominates at short distances, plus the linear term which dominates at large distances. Okay. So let's now move to the slide and see what is the shape of this potential. So this is what we just derived, okay? And then you can, of course, plot this potential as a function of distance in Fermi. And so the dotted line you see here is the short distance component, which is relevant and negative only at very short distances. So we are a fraction of a Fermi, essentially. And then we have the linear term, which goes like this, okay? So when you combine the two, at the end, you get this kind of potential, okay, which is attractive below this point and repulsive above this point. Okay. Now, why is this relevant? Because the non-relativistic QCD potential has been extensively used to obtain predictions for the spectra of the charmonium and the bottomonium. You remember yesterday I showed you for the charmonium there were yellow boxes and green boxes. The yellow were those experimentally observed, and the gray, sorry, were those expected by theory but not yet observed. So all these expectations, okay, have been obtained by using this very simple non-relativistic potential, okay? But the states are still waiting to be discovered experimentally. And this potential is relatively accurate for the charmonium, but it is much more accurate for the bottomonium, okay? Because the non-relativistic approximation is even better due to the high mass of the bottom quarks. And the best agreement with data is found with this value of the string tension, so the K factor here, 1 GeV over Fermi. And this provides a further evidence for the presence of a linear term in the potential, which is the one indeed responsible for the color confinement. Okay, so again, if you are able to fit your experimentally observed state with this kind of potential, which includes this term here, then essentially you are proving that this term is important, okay, is needed, and this is the one responsible for confinement, as we've seen yesterday. Now, let's now talk about hadronization. Okay, so we start for a simple process such as this one. So we have an electron and positron that annihilates into a quark-antiquark pair. Okay, suppose you have you are working in an electron-positron collider, and you can of course obtain these kind of events. Now, due to energy momentum conservation, the two initially free high energy quarks that are produced in this collision have to be produced back to back in the center of mass system. Okay, so the total momentum must be zero clearly. Okay. Now, what happens as now these two quarks antiquarks separate each other? As they separate, so they propagate in space, the color field, as we have seen yesterday, is squeezed into a flux tube, okay, with an energy density of the order 1 GeV over Fermi. But then, as soon as they separate even more, so as soon as the separation increases, the energy stored in the color field becomes sufficient to produce a new QQ bar pair from the vacuum, okay? And the original color field breaks into two smaller strings. So what is going on here? The quark and antiquark, which have been produced in the E plus E minus annihilation, are produced back to back, and they separate each other. They are traveling in opposite direction. As soon as they get more distant, the potential between them increases, as we've seen linearly. Okay, at a certain point, the value of this energy potential becomes equal to the mass of a new quark-antiquark pair. Okay, by energy mass correspondence, E equal mc squared. And when this happens, okay, then it is energetically possible that this energy is converted into the creation of a new pair of quark-antiquark from the vacuum. And when this happens, then you get now two strings. Again, now this quark-antiquark pair tend to get far away. And so each of those, when the energy becomes sufficiently high, again, generate a new pairs of quark-antiquark. And so you split once more your strings, okay? So at the end, you obtain a relatively large number of quarks in this side and a relatively large number of quarks in the other side, okay? And when now the energy of these quarks goes below some threshold, okay, so you cannot create new pairs from the vacuum, then the quarks combine inside hadrons. And what you observe from the experimental point of view is a jet of hadrons from in one direction and another jet of hadrons in the other direction. Okay, where clearly now hadrons are colorless objects, as we have seen yesterday. Okay. So this is now again the process of hadronization. So due to color confinement, the original QQ bar cannot propagate freely, okay? And in fact, what you observe at the end are jets of colorless or hadrons. And this process is called hadronization or also quark fragmentation, okay? It's like two quarks are fragmenting in a bunch of hadrons.
Una domanda.
Sì.
Qua vedo nella figura che ci sono anche gli stati a 3 quark. Questo processo di hadronizzazione vede soltanto formazione di stati a 2 quark oppure sul serio sono possibili anche a quelle più quark?
Sì, anche a 3 quark. Tu alla fine produci mesoni e barioni. Cioè alla fine i quark, allora, quando ne hai creati talmente tanti che l'energia a questo punto non è più sufficiente a crearne di nuovi, ok? Perché l'energia chiaramente è finita, è quella che hai prodotto nel centro di massa di quell'interazione, quando hai annihilato il positrone e l'elettrone, a quel punto non puoi più produrre nuove coppie e a quel punto i quark si ricombinano come meglio preferiscono e quindi in singoletti di colore possono fare solo quello e sostanzialmente in mesoni e barioni. Poi può anche succedere che vengano fuori anche dei hadroni esotici come quelli che abbiamo visto ieri, ma sono eventi molto più rari chiaramente. Quindi di fatto i quark a un certo punto, quando non possono più splittare, per confinamento si confinano all'interno di hadroni e quindi vengono proprio prodotti a questo punto sia mesoni che barioni, quindi sia stati QQ-bar che stati a 3 quark.
Ok, grazie.
Ok. So the hadronization of the original QQ-bar pair results in 2 jets of hadrons, which are emitted approximately along the direction of the original quark-antiquark. Clearly, for momentum is conserved in this, okay? So at the end, the direction of this jet must be, when you sum all the momenta here, must be the same of the original momentum of the original quark and the same for the other one. Okay, so the direction of the 2 jets is also back-to-back and corresponds essentially to the direction of the produced quark-antiquark pair, which is not necessarily the same direction of the electron-positron, you see. This could be in any direction, but the important point is that the momentum is conserved, so the two are produced back-to-back. Now, more in general, hadronization is the process by which a set of colored partons, so the quarks essentially, or gluons, as we will see, evolve into a set of colorless objects, so the color singlet hadrons. Now, back on this string break process here, okay, how we can interpret this. We have, of course, a clear analogy with the magnets, okay? So the breakdown of the color flux tubes and the formation of new QQ-bar pairs, as you see here. So we start from 1, then we have 2, then we have 4, etc. As the distance between the parent quarks increases sufficiently, can be compared with a more familiar example of the broken magnet. If you try to isolate the north and south pole of a magnet, you will never succeed because, as you know, if you break the magnet, then a new pair of poles is created automatically, okay? And this is essentially the same thing that happens here. Is a nice analogy to show this. Now, is the probability of creating different quark flavors the same? Clearly not, because it strongly depends on the energy that it is available, and so depends on the mass of the quarks. So due to higher mass of the strange quark compared to that of the up and down quark, a strangeness suppression in this process with respect to up and down is observed, okay? It is expected and also observed. As soon as so it is much less probable that in such a string breaking, you create a strange quark, okay? Usually you only create up and down quarks because they are much more energetically favorable. And in particular, the ratio of production of strange quark with the up or down quark is of the order of 20, maximum 30%, okay? And how can you observe this? Because at the end you observe hadrons. Of course, you cannot observe quarks in your final state, but you can observe hadrons. But you know that, for instance, the strange quark will be encoded in some kaon, for instance. and up and down quark in pions. So if you measure the ratio between produced kaons and pions, so you can infer the ratio between produced strange and light quark in this string fragmentation process. What about heavier quarks, so the charm quarks? Now this is completely suppressed because of energy conservation, of course. So the suppression of charm quarks is of the order of 10 to the minus 11. Okay, so essentially you will never get charm quarks, charm-anti-charm pairs from this string breaking process. Okay, and so heavy quarks can therefore be produced only in the perturbative stage and not during the fragmentation process. Now, let's see what experimentally one observes. So this is an event displayed by the OPAL experiment at LEP. LEP, let me remind you once more, was the electron-positron collider at CERN in the same tunnel that is now hosting the Large Hadron Collider. So electron-positrons were colliding in the first stage of LEP at 91 GeV. Okay. Can some of you tell me why 91? Is this a random number or there is a reason for this?
Well, I don't remember the mass of charm quarks, but I believe this is the minimum energy to obtain 2 C quarks. Or
No,
something.
C quarks is much lighter. C quark is 1.3 GeV, so you just need less than 3 GeV in that case.
Okay, sorry.
No, you need something much heavier here. Can you infer what can be this?
91 GeV.
Mm-hmm.
Maybe. No, don't know. Bottom? Forse erano?
No, bottom sono troppo leggeri pure, sono 4 GeV qualcosa. No, non riguarda i quark.
Ok.
Vabbè, chiaramente il top è 173, quindi non gli fa lo stesso, chiaramente. Fino al bottom sono troppo poche, insomma, la massa è troppo leggera, quindi non è questo. In realtà, diciamo, questo collider, il LEP, in questa prima fase era tunato proprio a produrre nel centro di massa un'energia di 91 GeV per produrre, appunto, quale particella? La particella di 91 GeV.
Sì. 91 GeV.
Non mi viene niente in mente? Ne abbiamo sicuramente parlato nella primissima lezione quando ho fatto l'introduzione al modello standard.
91 GeV.
Ho un po' barato, sto guardando la tabella e vedo il bosone Z che è 91 GeV.
Esattamente.
Okay.
Cioè, il LEP in effetti è stato proprio creato, ideato, realizzato e creato e ha lavorato per 20 anni per studiare con precisione i bosoni elettrodeboli, quindi il bosone Z in particolare in questa prima fase, e poi i bosoni W+, W- in una fase successiva in cui l'energia del centro di massa è stata aumentata fino a 200 GeV. Questi bosoni, come studieremo quando parleremo dell'interazione debole, sono stati scoperti agli inizi degli anni 80 a una macchina completamente diversa che era il Super Proton-Antiproton Collider, ma lì si è fatto una scoperta con una manciata di eventi, cioè si sono visti 4 W+, 10 Z0 per dire, ok? Ma per studiarli con precisione serviva una macchina di alta energia capace di produrne a miliardi, ok? Miliardi non so, ma sicuramente milioni. E quindi diciamo il LEP fu proprio tunato in questa prima fase proprio a 91 GeV proprio per produrre risonanze Z0 in grosse quantità e quindi per poter fare studi di grande precisione. Tutto questo ovviamente lo studieremo più avanti. Ok, so back now to our hadronization business. So what you see here is a typical 2-jet event from the OPAL experiment at LEP, okay, which was operating in the 90s essentially. So you see here we have a bunch of 2 bunches of hadrons, okay, which release energy in many subdetectors of the OPAL detector, okay, and they are back-to-back as we expect. So these hadrons originate from the fragmentation of this Q-Q bar pair originated in the annihilation of the electron positrons, okay. But even more complex processes have been observed, okay, such as those 3-jet events. And the 3 jet events are now a clear indication, or even 4 jet events, are now indication that the hadronization occurs not only from quarks, okay, but can be initiated also by gluons. This is an higher order process compared to this one, where now a quark radiates a gluon, like a Bremsstrahlung radiation, if you just to make a comparison. But the gluon then is a colored object, so it cannot propagate freely, and so also the gluon must hadronize. And this is why you observe 3 jet events like this, okay, or even 4 jet events. Now, and in fact, this was actually the way gluons were discovered. Okay, so gluons were in fact discovered through the observation of 3 jet events, which can only be interpreted in this way. All right. And this occurred for the first time at the Petra electron-positron collider at DESY. DESY is a laboratory in Hamburg in the north of Germany. And the discovery occurred in 1979. So you see here essentially the very first 3 jet event observed by the Tasso experiment at the Petra collider. And this was the first experimental proof of existence of gluons. Now, do jet produced by quarks and gluons are expected to be the same, with the same features? Actually not. So QCD predicts that quarks and gluons fragment differently due to their different color charges, of course. So gluons jet are expected to be broader than quark jets. The multiplicity of hadrons in gluon jets should be larger than in quark jets of the same energy. And particles in gluon jet are expected to be less energetic. Okay, so the jet produced by a gluon are broader, have a larger multiplicity of hadrons, and those hadrons have less energy compared to a jet initiated by a quark with the same energy. Okay, and all these features, which are predicted by QCD, are also experimentally verified. Now, a powerful tool to study QCD is indeed through E+ E- annihilation. And there are 2 important reasons, okay? So one of the main advantages of studying QCD through E+ E- process, so where you create a QQ-bar pair, is that this is a QAD process, of course. It is an electromagnetic process. You are creating a quark pair through a photon, okay? And so, and QAD, we know we can apply perturbative techniques, so we can calculate the matrix element of this process very, very precisely, okay? Clearly, when you look now at the reaction in the center of mass, okay, we have 2 elementary particles colliding in the initial state, the electron and the positron, but in the final state, what you observe are instead the jets of hadrons in the direction of the original quark-antiquark pair, okay? And the other advantage is that compared to hadron-hadron collision, where there is compared to hadron collision, there is no background arising from the remnant of the colliding hadrons that typically also evolve into jets. So what does it mean? Suppose you are now colliding proton-antiproton instead of electron and positron, then clearly you will also produce the QQ-bar pairs, which will evolve like this in a back-to-back pair of jets. But proton and antiproton are not elementary objects. They also contain other quarks, the remnants. And these quarks at the end have to hadronize as well. And so at the end, in your final state, you will have many different hadron jets, and it will be now difficult to distinguish the signal from the background. Okay, so if instead you use E+ E- in the initial state, we don't have this problem anymore. So there are at least 2 main advantages of studying QCD in E+ E- collisions. Now, if you remember, we have studied the annihilation process, electron-positron into mu plus mu minus in QAD, okay? And we found that the cross-section has this kind of angular dependence. So it goes like the 1 plus cos square of theta, where theta is, okay, the analogous of this angle when you produce a mu plus mu minus. Now, if we assume that quarks are also spin 1/2 particles, okay, then we expect that the angular dependence for the process electron-positron into a quark-antiquark must be the same, okay? Here I put the proportionality because clearly the coupling constant is different, etc. But at least the angular dependence should be the same. Suppose that quarks are also spin 1/2 particles, And this can be verified experimentally. So you see here data, experimental data, as a function of the modulus of the cosine theta. And the angular distribution of jets produced in the plastic annihilation indeed is consistent with the expectation of 1 plus cos squared theta. Okay, and this in a sense provides already a proof that quarks are indeed spin 1/2 particles. Otherwise, you would have gotten a completely different angular distribution. Okay. However, let me make a comment here. Okay, so this was not the first proof that quarks are spin 1/2 particles. The very first proof came actually in the late 60s through the experimental verification of a relation, the Cullen-Gross relation in deep inelastic scattering. And this we'll be studying next week. Okay, so clearly when you now study quark hadron jets, it was already known that quarks are spin 1/2 fermions. Okay. Now, still a couple of comments on these results here. So since quarks and anti-quark hadronize into jet of hadrons, the process is usually denoted as E plus E minus into hadrons. Okay, you will not see here QQ bar because clearly at the end you will not observe a quark and anti-quark, but you only observe jets of hadrons. And the other comment is the following. Since it is usually not possible to identify which jet came from the quark and which jet came from the anti-quark hadronization, this ambiguity is expressed by representing the differential cross-section as a function of this absolute value of the cos theta. Okay, so essentially here you include both possibilities. Now, let's now consider the integrated cross-section for the QED process E plus E minus into mu plus mu minus. Okay, if you remember, you have in your slides for QED, the QED chapter, this was the result. Okay. And what is now the corresponding total cross-section for the QED process E plus E minus into QQ bar? Okay, so clearly it must be essentially the same apart from a few differences, minor differences. So first of all, we have an additional factor of 3 here, and this accounts for the sum over all possible color combination in the final state. So here you are producing a QQ bar pair, so this can be produced either as a red anti-red, green anti-green, blue anti-blue. And these are the only 3 possibilities because in the initial state we don't have quarks, so the color is 0, and so the total color must be 0 also in the final state. Okay, so you need to have a color and its anti-color. And then the other difference, of course, is the electric charge. Okay, we know that quarks have a fractional electric charge compared to the electron. So this can be either the square root of 1/3 or the square root of 2/3, depending if it is an up-type quark or a down-type quark. Okay, now there is, however, a subtle here. So since the quark and the anti-quark hadronize into jets of hadrons, it is in general not possible to identify experimentally their flavor. So we don't know if the fragmenting quark was an up quark, was a down quark, or was a strange quark. This we can never. It's very hard to infer. Okay, you can make a hypothesis, but it's very hard to infer from the data. And so for these reasons, the cross-section for the E plus E minus into QQ bar pair must be expressed as the sum over all possible quark flavors. So we talk about inclusive cross-section in this sense. Okay, so essentially we have to sum up this guy, okay, to all possible quark flavors that can contribute. Of course, this depends on the energy available. Okay, if it is a low energy process, then sure you cannot produce bottom quark or chum quark, but only light quark. So it depends, of course. So the number of terms here in the sum depends on the energy available in your process. Okay, but now we can take now the ratio between this guy here, so E plus E minus into hadron divided by the E plus E minus into mu plus mu minus. So we take the ratio of this cross section, and if all this discussion makes sense, the ratio is simply given by this factor here. So 3 times the sum over the squared charge of the available flavor at that particular energy. Okay. So let's see now these. Let's distinguish now a few cases. So suppose that the center of mass energy is quite low, so it's below 3 GeV. Okay, that means it's below the threshold for creating a J-psi, for instance. Then the only available flavor at this energy can be up, down, and strange. So you calculate now this ratio, just for with these three contributions. So you just have to take the sum of the square charge for the up quark, the down quark, and the strange quark. And you get, for this ratio, a value of 2. If the energy in the center of mass is above the Gibbs mass, so above the threshold for producing Cham quark, okay, then you have to add an additional term here, also including the Cham quark possibility, okay, which is this 4/9 term. And so still we have the factor of 3. So at the end, you end up, in this case, for this ratio of cross-section, a value of 3.3 or 10 divided by 3. If the energy is even above the upsilon states, okay, so you are now able to open the channel for the bottom quarks as well, you add this additional last term here, okay, which is the square of the bottom quark charge, and the result will be 11 divided by 3, or 3.7. Okay, clearly it makes no sense to go beyond this because the top quark is far too heavy, and as we've seen, it will never hadronize, okay, it will never be contained into a hadron. However, this is not a very precise guess, because one has also to consider higher order processes that can contribute. And in particular, at first order, the higher order processes are those three here. So we have one already from the electromagnetic process E plus E minus into mu plus mu minus, where a photon is radiated by one of the two muons. We have now in the QQ bar case, but in the QQ bar case, a quark can also radiate a gluon, okay? Because now this also QCD can also take part of the game. So while the first two are simply QED corrections and are relatively small, because we know that the fine structure constant is small, the latter one cannot be neglected. Okay, so this contributes quite significantly because we know that the alpha strong is much the value of the alpha strong is much higher than that of the electromagnetic coupling constant. Okay, and the correct way to include this first order QCD correction is to add in our ratio this alpha S over pi ratio. Okay, so if there is no correction, this guy goes to 0, and you just have 3 times the sum of the squared charges. If you want to take into account the first order QCD correction, you have to add this ratio here, this term here. And once you do so, then you finally get an incredibly high agreement with experimental data. Okay, so here you see the ratio between these two cross sections as a function of energy. So before looking at the data, let me show you that we have some low energy resonance here. Then we have the J-psi resonance, which is very, very narrow, as we will see later on. So the reason why it is not so narrow, we understand later on. Then we have the excited state of the J-psi below the D-meson mass threshold, which are also very narrow. Then we have other higher energy charmonium resonances. Then we end up now at a higher level. Okay, now we are in this range of energy. So we made a step here. So and we have at the bottom here around the 9.5, 10.5. We have also the very narrow upsilon resonances. Okay, and then we have the final step here. So in the first step, we just have up down a strange quark. Okay. Here we also allow for the Cham quark, and because we are now above the charmonium, and here we also allow for the bottom quark because now we are above the bottomonium states. Okay, so the dotted line here that you see are those without the QCD correction. Okay, and you see that the agreement with data is not so good at the end. But if you allow for this very simple first order QCD correction, then the prediction is this full line. And you see that it matches very, very well the experimental data, okay, for all three cases. If, on the other hand, there would be no color degree of freedom, so essentially just one color, the prediction would be right here, so completely off compared to the experimental data. So this agreement here in this ratio is a very, very strong proof of the existence of three colors in QCD, okay? So let me say this again. So this striking agreement provides another strong evidence for the existence of the three color charges, so a number of colors equal 3. Without these additional degrees of freedom, the prediction of this cross-section ratio would be a factor of 3 smaller, and so completely incompatible with experimental data. Now, these plots arrives up to 40 GeV. What is beyond that? Well, when we go beyond that, the annihilation with the exchange of a zeta boson, the one that we were discussing before, starts to be significant and competitive together with the production through the photon. Okay, so you have a plus E minus that goes into a photon at low energy, but can also go into a Z boson at high energy. And so the two processes actually interfere, okay? And so you have to take into account also this interference when you want to make predictions above 40 GeV, okay? Now, what time is it? Okay. Still back to QED. Okay, if you remember, we discussed the vacuum polarization in QED. Okay, so essentially we have an electron, but an electron at any time can radiate a photon. The photon at any time can create a loop of electron-positron. Another photon is created, and so essentially this process goes spreads. So overall, you have a cloud of electrons and positons around your original electron. Okay, and these clouds, due to electrostatic potential, at the end screens the original electric charge of the electron, if you remember, okay? So this was indeed the vacuum polarization in QED. So the positrons tend to be closer to the electrons so that the electric charge is screened. And as a consequence, if you remember, okay, the value of the electric charge that you measure depends on how deep your probe enters this cloud of electrons and positrons, okay? And in particular, we've seen that for low energy processes, the probe stays far away, the charge is highly screened, and this corresponds to our standard value of the alpha strong. However, if you make your probe going very, very inside this cloud, okay, the charge that it feels is IR, and asymptotically this diverges, okay? And this was what we also discussed in the when we introduced the renormalization of electric charge, if you remember. Okay. Now, this is for QED. What about QCD? So, in analogy to the vacuum polarization in QED, also quark-antiquark pair screen the color charge. So we have essentially the same effect here, okay? But now with the quark-antiquarks. However, since also gluon carry charge, there is a concurrent effect which arises from gluon loops that you see here now, okay, which acts in the opposite direction. It is called anti-screening, okay, and in fact it leads to an increase of the color charges at large distances. So it is opposite to the screen effect. So essentially in QCD we have both effects, okay. The analogous of the QED1, okay, where the quark-antiquark pair screens the original color charge of the original quark, but since gluons also carry charge, we have a concurrent and opposite effect, okay, which at the end is the dominant, okay. So it turns out that in QCD, the anti-screening effect is stronger than the screening effect. So this is what dominates at the end, okay. And so we have now essentially the opposite trend, okay. When we look our probe from a very large distance, so for low energy processes, the intensity of the coupling constant is much, much higher. So alpha strong can be as large as 1. If instead we get closer and closer and closer, so we increase the energy of the process, okay, this goes asymptotically to 0. Okay, and this is, so here we can essentially identify the two opposite regimes of QCD. This is the regime of confinement that we studied yesterday, where the coupling constant is very large, order of 1, and this corresponds to low energy phenomena, okay, and so large distance phenomena. And in the opposite, we have a region where the alpha strong is very, very small, so it can now be used in perturbative techniques to make perturbative calculations. And this is the reason where it is called the asymptotic freedom. That means that the strength of the strong interaction is so weak that essentially the quarks behave as free particles. They don't interact with each other, essentially. Okay, so these are the two extreme behavior of QCD at large distance and at small distances. And of course, we have done a logarithmic decrease in between, which is altogether essentially the opposite behavior of what we have seen in QED. So still on this, okay, this slide just in a very simplified picture shows this concept. So when you are close to your quark, you only see 4 gluons. So the charge is only barely screened, anti-screened. But as soon as you get far away, now you go to this larger circle, then you have 8 gluons. If you go far away, you get 16 gluons. And so the far away you go, the more gluons you have, and the stronger is the anti-screening effect. Okay, this is just to illustrate the process. Now, and we have now, of course, the same consequence we can draw as the one we did for QAD. So in analogy to QAD, although with the opposite trend, the QCD coupling constant is not a constant, but it is also a running constant. So its value depends significantly on the energy scale. It is large at small energies, okay, which is the region of confinement, and it is small at high energies, and this is the region of the asymptotic freedom. So we can also here, in the same way we did for in QAD, calculate the Q-square dependence of the alpha strong. So how the alpha strong essentially varies with the transfer momentum, or more in general with energy, okay? So as for QAD, the general dependence of the strong coupling constant on the momentum transfer is expressed by the renormalization group equation, which are the same kind as those that we already seen in QAD, okay? In which the coupling is expanded in powers of logarithm of Q squared divided by mu squared, where mu is an arbitrary scale. Suppose, I don't know, 10 GeV or 100 GeV, whatever. Now we have a B factor here, okay? And the B factor depends on the number of loops. So due to the gluon-gluon self-interaction in QCD, there are clearly additional loop diagrams compared to QAD, okay? So this diagram, of course, you cannot have in QAD because photons do not interact with themselves, okay? So now we can invert this relation, okay? So we obtain alpha strong from this, okay? And this gives us the Q square dependence of the QCD coupling constant, okay? So it is the alpha strong at a given scale mu, okay? And then we have this logarithm dependence with the Q square. The B factor, which is here reported, depends on the number of loops, etc. In particular, it is given by 11 times the number of colors minus 2 times the number of quark flavors divided by constant, okay? And so essentially, once the coupling constant is known at a certain scale mu, then this expression allows you to calculate its value at any other energy value, any other energy scale. This is called the QCD evolution of alpha strong. So back to on this B factor, okay, so we can now substitute some numbers here. So the number of color, we know it is 3, and we also just show how it is experimentally proved. The number of flavor, okay, suppose it is the active flavor can be at maximum 6, okay? We know there are 6 quark flavors in maximum. And so when you substitute this number, it turns out that B is a positive number, okay? And as a consequence, the alpha strong decreases logarithmically, okay, with increasing Q square. Whereas as we've seen in the QAD coupling constant increases logarithmically with increasing Q square, okay? And so essentially this is consistent with the dominance of the anti-screening effect in QCD, okay? Now, how can we measure alpha strong? There are many ways. Many ways have been exploited in the past. Here, just let me list some of them. So through the study of hadronic decays of the tau lepton, through the spectroscopy of the charmonium and bottomonium states, in deep analysis scattering, this we will see next week, in jet production of E+ minus annihilation, and several others. And this plot here essentially give you a collection of all experimental data based on very different processes, very different experiments, okay? And altogether, they reproduce this logarithmic decrease of the alpha strong with increasing transfer momentum, okay? Just to take you a couple of values. So the most precisely determined value of alpha strong for E+ minus collider, so essentially at LEP, okay, are the following. Okay, so one measurement has been done at the mass of the Z, so at 91 GeV, and this value is order of 0.12 something. And another measurement is made now at a much lower scale, so at the mass, sorry, this is not the Z, this is the tau. I have to correct this. This is the tau lepton, okay? And as soon as you go indeed to a lower energy, you get a higher value of the alpha, so 0.33 in this case. These results are very precise, okay, and have been obtained at next to leading order. That means including QCD corrections up to the 4th order, based on the calculation of something like 20,000 diagrams. So huge calculation is implied here, okay? And the errors which are reported here are dominated by the experimental uncertainties. So in this case, the theoretical calculation is more precise than the present experimental accuracy. And this gives you just some idea of measurement of the alpha strong that have been made at lab, okay, through different processes, okay. You see for each process the corresponding value with its error bar, and you have also some spread. And in particular, in the bottom, you see the world average provided by the particle data group. This was back in 2001, okay, at the mass of the Z0. Ok, direi che possiamo fermarci qui per una pausa.
Ok, posso riportare un attimo nelle slide precedenti?
Dimmi dove?
Ancora indietro? Qua. L'alfa square, alfa di S alla mu quadro, cioè di mu quadro. Mi sono perso che cosa sia. È il valore
della costante di accoppiamento forte, però ad una scala ben precisa, in realtà arbitraria. Cioè tu supponi da un esperimento di misurare alfa strong, metti a 10 GeV quadri, ok? Quindi lo sostituisci qua dentro e questa formula qui ti consente di calcolare alfa strong a qualsiasi valore della scala, a qualsiasi Q quadro. Si chiama appunto evoluzione di QCD, ok?
Ok.
Quindi metti per esempio qui il valore che è misurato nel decadimento del leptone tau, e con questa cosa qua ti può calcolare, e in effetti diciamo questa curva continua che vedete è proprio ottenuta da questa relazione qui, ok? Da questa forma, ti può calcolare il valore a qualsiasi valore di Q quadro e confrontarlo con dati di altri esperimenti ad altre energie. Allora, vediamo un po' che ore sono. Vabbè, ripartiamo alle 10:10.
Va bene.
Ok.
Vabbè. Scusi, prof, posso fare una domanda anch'io?
Certo.
Noi, un attimo concentrarmi perché è un po' complicato da spiegare. Praticamente noi quando parlavamo di particelle virtuali, per esempio per i fotoni così, parlavamo di mancata conservazione dell'energia che poi viene riportata al vertice, eccetera.
Sì.
Ma qui invece abbiamo parlato di confinamento per il fatto che i gluoni portano della carica di colore, però detto così mi verrebbe da dire che esistono solo sotto forma virtuale questi gluoni.
Allora, no, nel senso che, ti faccio vedere. Allora, i gluoni che stanno in un loop sono chiaramente virtuali, ok? Quindi qui vale esattamente lo stesso ragionamento che abbiamo fatto per i fotoni. Ma in un processo di questo tipo qua, questo è un gluone reale. È come l'emissione di un fotone reale da Bremsstrahlung, per esempio. Quindi questo è un gluone reale. Il problema è che siccome è colorato non può propagarsi liberamente, ma deve subito hadronizzare e quindi subito creare un jet di hadroni.
Ah, ok. Quindi, ok, va bene.
Ok? Così come questo è un fotone reale.
Ok. Grazie.
Niente. Allora, riprendiamo.
Prego.
Allora, adesso fatemi riprendere una cosa che avevo soltanto accennato qualche tempo fa quando abbiamo parlato dei mesoni, e adesso ne capiremo meglio il significato. Se vi ricordate, quando vi ho mostrato la tabella dei mesoni, vi ho parlato di questo decadimento del mesone φ, che può andare in 2K o in 3π. Il decadimento in 3π è rappresentato da questo diagramma e ha un Q-valore molto alto, 600 MeV, mentre il decadimento in 2K, che è rappresentato da questo diagramma, invece ha un Q-valore molto basso. Quindi vuol dire che lo spazio delle fasi è molto più favorevole per questo decadimento che non per quest'altro decadimento. Ma in realtà quello che si osserva è che la probabilità di questo decadimento è molto molto più alta dell'altro. Quindi c'è qualcosa di strano qui, ok? E vi avevo accennato che diciamo, la ragione di questo sta nella cosiddetta OZ rule. Vediamo adesso di cosa si tratta e cosa c'entra la QCD. So, the 3-pion decay, this one, is represented by a disconnected diagram. You see, it is disconnected here. Now, being the phi meson a color singlet state, because it is an hadron, so it is a color singlet, the initial and final state cannot be connected by a single gluon. Okay, so because the gluon carry color. So if you would connect this diagram with a single gluon exchange, this will never work. You would, of course, not conserve gluon color. Okay, because you start from a color singlet here, and you end up in a color singlet also there. So this fact is generalized by the Okubo-Zweig-Iizuka rule, so the OZI rule in brief, okay, which said the following, that disconnected diagrams require more than one gluon to be connected, resulting, of course, in an overall suppression of the process compared to connected diagrams. This is clearly connected diagrams. It does not need to add more gluons here, okay? So how many gluons are exchanged here then? So let's now infer by charge conjugation conservation in strong interactions, okay? So the charge conjugation of a phi, as you know, is -1 L plus S. The phi is a low-lying meson, so L is equal 0. It is a vector meson, so S is equal 1. And so overall, the phi is a sense, is an eigenstate of G with eigenvalue -1. What about now the charge conjugation of the exchanged gluons? So suppose we exchange two gluons, okay? If you remember for gauge bosons, they are eigenstate with eigenvalue -1. So if you have two gluons, it is -1 to the square, and it is a +1. So if you would connect these two half diagrams with two gluons, you would violate charge conjugation conservation. What about three gluons? Okay, in this case you get -1 to the third, so you get the proper sign, -1. Okay, and that means that indeed this decay can proceed with at least the exchange of three gluons. Okay, now how does this process looks like in detail? This is the decay. So we start from a phi meson, which is an SS bar. Okay, we end up with 3 pions. Okay, pi plus, pi 0, pi minus, and we connect these two parts by the exchange of three gluons. And each gluon is at the end responsible for the creation of a quark-antiquark pair. Okay, you see each of these splits into quark-antiquark pair. So at the end you obtain three mesons. This is instead the other process, the one that goes into chaos. So we start from the phi, SS bar, okay? In this case, we just need to create a UU bar pair, okay? Because the SS bar that go into the chaos is already available in the initial state. Now, by comparing the two, of course, the first thing that is clear is that we have, of course, many more vertices in this decay than in this one, okay? But the appearance of a greater number of vertices is not the only reason for the suppression. There is also a consequence, okay, which is related to the fact that alpha strong is a running coupling, okay? So the fact that it decreases with increasing energy. And the reason is the following, okay? So for the 3-pion channel, the gluons must have a high Q square. We call them hard gluons. because they are produced in the decay of a rather massive meson, which is the phi of order 1 GeV. So the mass of the meson is essentially distributed in terms of the energy of these gluons, which are order 300 MeV each, so quite hard. And since it is, in a sense, a high energy process, okay, the coupling constant will appear small to these gluons because it is running. And this contributes to lower the importance of this mode in the matrix element of the decay. What about the other? In the 2K channel, only 2 soft gluons are required, which share just the energy to create a single U bar light quark pair. Okay, so you just need soft gluons here, because the much heavier S bar pair is already present in the initial state. Okay, so they are thus lower in energy than in the three gluon case that we've seen before, and so they contribute to the matrix element of the decay with a higher value of alpha S. And this, of course, results in a higher probability. Okay, so we have the combination of these two effects. The first one is that we have more vertex number, and each vertex is addition adds a suppression factor. But then we have also a reason due to the running alpha S. Okay, hard gluon works with smaller alpha S. Soft gluons see a higher alpha S, and so this corresponds to a higher probability. What about the JEPSI case? So as I was mentioning before, let me go back here. Here, you see that the JEPSI, okay, the JEPSI resonance is dotted here, okay? It is so narrow that it is even hard to draw in this plot here. So let's now see how narrow it is and why it is so narrow. Okay, so the width of JEPSI resonance is very small. It corresponds to an extraordinarily long decay time for a strong process. So this is the width. You see how small it is. And so it's a fraction of keV, and this corresponds to a decay mode, the decay time of 10 to the minus 21, okay, which is extremely long compared to the standard strong decay time. So it appears that something must inhibit the decay of the JEPSI. What is the problem here? So in the most obvious decay for the JEPSI, which is a CC bar meson, would be clearly into a D plus D minus pair, okay, as depicted in this diagram here. This would be the easiest way to decay. However, as we have seen, this is energetically impossible. It is energetically forbidden because the mass of the JEPSI, which is 3.1 GeV, is less than the sum of the mass of the two final state D mesons. Okay, you need something around 4 GeV at least. So this decay is energetically forbidden. Cannot happen. In this respect, the JEPSI meson behaves differently compared to the phi meson, because while the phi meson is massive enough to decay into strange mesons, so the phi decays in fact with a very high percentage into pi plus, k plus, k minus, the JEPSI is below the threshold for decaying into a pair of charmed mesons. Okay. So this is not the possible decay because it is energetically impossible. Okay. However, this explains only partially the narrowness of the JEPSI decay. One would in fact expect that it should decay strongly and very quickly into pions, because if you sum up the mass of pions, you end up with a very large phase space. Okay, is just a few hundred MeV compared to 3 GeV. Okay. However, this decay is suppressed by the Olzi rule. As you can see, the diagram is disconnected for the same reason as it was for the phi decay. Okay, and so you need again the exchange of 3 gluons in order to connect properly this diagram and to create the final state mesons. And so indeed it is the combination of these two effects. So the combination of the Olzi suppression for this decay and the fact that JEPSI is below threshold for a much straightforward decay into charmed mesons that explains the narrowness of the JEPSI width resonance, the JEPSI width. And of course, it's extraordinarily long decay time. Okay, so the running alpha strong plays a crucial role also in this kind of decays through the Olzi rule. Now, still on alpha S. So when we work in the scale of order of 1 GeV, alpha strong is quite large. It's very large actually. Is of the order of 1. Okay, so in this regime, QCD is non-perturbative. So this is the regime, the non-perturbative regime of QCD in particular. Okay, so the theory becomes extremely complex. You cannot make perturbative calculations, and therefore it becomes not predictive. That's the main difference, the main problem of QCD compared to QED. Okay, the low energy QCD process, which are confinement, hadronization, hadron structure, hadron spectroscopy, etc., are not calculable from first principles, starting from the Lagrangian QCD. Okay, but they need to be measured. So the theory cannot help here because we are in a non-perturbative regime. And the interpretation of the experimental result usually relies on models, so on QCD-inspired phenomenological models. The Lagrangians that are typically used are called effective Lagrangians because they have many ingredients of the QCD Lagrangian, but they put some model assumptions inside. Okay, you cannot use first principle to make prediction on all these low energy phenomena. On the other hand, if you now work at high energy, at high transfer momentum, so above 100 GeV, the value of Armstrong is now quite small, order of 10%, 0.1. So in this case, perturbative methods can be used, and this is in fact called the perturbative regime of QCD, PQCD. In this short distance regime, very precise QCD calculation can be performed, and the theory becomes very predictive. So this is the regime of asymptotic freedom, as we have seen before, where indeed quarks interact very weakly and can be considered as quasi-free particles. Now there is a caveat, however, because although alpha S of 0.1 is sufficiently small to apply perturbative methods, it is not so small. It is not as small as the defined structure constant. Okay, and so in this case, although you can still apply perturbation methods, you cannot neglect higher order corrections, as we do in QED, if you remember. In QED, you have already a precision of 1% if you just consider the zero order level processes, okay? And you need to take into account, let's say, the second, third order process to have a very precise prediction. Here, you cannot neglect the higher order, okay, because they're not so small. There's higher order diagrams that need to be calculated at next leading order, next to next leading order, and so on and beyond, okay, in order to have accurate predictions. And these calculations clearly are extremely complex. So one way out this is a technique that was developed in the last decades, and it is the lattice QCD, okay? This is a non-perturbative approach, okay, which is based on computational techniques that allow the QCD calculation from first principle now, okay, although in a non-perturbative regime, but based on a discrete grid of space-time. So essentially, the technique is the following. Instead of having a continuous space-time, you discretize your space-time into this kind of four-dimensional grids, okay, where each row is a gluon and each node is a quark, essentially. And you make a calculation in this discretized space, which is much simpler, although it is still very complex, by the way, okay? And then, in order to get a physical result, so the result of this discrete quantization, you have to then push in the limit of continuous spacetime. So at the end, you essentially take the limit of continuous spacetime, so essentially of vanishing lattice spacing in your result, and this is at the end your prediction, your physical prediction. Now, with this technique, lattice QCD is possible to calculate, for instance, the proton mass, which is a clearly non-perturbative quantity, from first principles, okay, so starting from the QCD Lagrangian, with the precision of a few percent. And also, valuable results are obtained in other non-perturbative phenomena, such as confinement, QCD phase transition, spectroscopy, hadronic matrix element, hadron structure, etc. So all these phenomena are non-perturbative, okay? So either you rely on phenomenological models or you apply lattice QCD, okay? Of course, there are limitations, and the main limitation is the computing power, because these calculations are computationally intensive, they are extremely complex, and for a single calculation, one may require several months of CPU, okay? And so, in fact, these calculations are usually performed by a farm of supercomputers. You need a huge CPU power. Ok, chiaro ragazzi?
Sì.
Sì.
Ok, Quindi vi faccio un esempio, diciamo, ci sono diversi gruppi teorici nel mondo che lavorano sulla lattice QCD, e così come uno sperimentale che vuole fare un esperimento deve richiedere per tempo, quindi mesi prima, anni prima, del tempo fascio a una macchina, un acceleratore. Per esempio, io ho bisogno di un fascio di protoni da 100 GeV per 3 mesi per fare il mio esperimento. Allo stesso modo, questi teorici devono fare una richiesta a questi farm di supercomputer per dire: io ho bisogno di fare questo calcolo, mi servono 6 mesi di CPU su questa farm di supercomputer. Okay? La precisione ovviamente, diciamo, della lattice QCD è aumentata notevolmente negli ultimi anni, okay? Quindi si è partiti, diciamo, 20 anni fa o qualcosa del genere con dei risultati molto approssimati, okay? E man mano che aumenta chiaramente la potenza dei computer si riesce a discretizzare sempre di più questo reticolo, a fare, diciamo, dei passi sempre più piccoli e quindi delle soluzioni sempre più precise e veritiere. Okay? Adesso andiamo a un altro fenomeno che è sempre legato anche qui al fatto che alpha strong è running, okay? È il cosiddetto fenomeno del deconfinamento e del quark gluon plasma. So, in ordinary matter, quarks, as you know, are confined within hadrons, and the atomic nuclei can be thought as bound states of protons and neutrons. This is standard nuclear matter. However, as the energy density is increased, a phase transition can occur to a state in which the individual nucleons lose their identities and the quarks and the gluons become free to move. So free to leave essentially the nucleon boundaries and to move across a volume that is larger than the compare of a nucleon. And this is a consequence, this is essentially the asymptotic freedom regime, okay? So if you go to very high energetic processes, then the alpha strong becomes very, very small, and the quarks and gluons behave essentially as a free particle, so they can move freely. They are not anymore interacting. Now, lattice QCD calculation suggests that this phase transition should occur at an energy density of the order of 1 GeV per Fermi cube. So this is a ratio between an energy and the volume. So if you're able to condense 1 GeV into a Fermi cube, then you are in the condition that allows this phase transition to ordinary nuclear matter into this deconfined phase, where quark and gluons are free to move. And this is essentially 6 times the energy density at the center of a heavy nucleus. Suppose you have a gold nucleus or a lead nucleus, okay? With a density of ρ0, then you need to increase this by at least 6 times in order to obtain the proper energy density that would allow this phase transition. Okay, and this corresponds also to a critical temperature of the order 160 MeV. Now, the circumstances are not just an academic speculation, but they are believed to have occurred in the earliest ages of the universe. So when at the fraction of time smaller than 1 microsecond from the Big Bang. When, of course, the energy density was so high that no hadrons could be formed. And so in that age, quarks and gluons were completely deconfined and very weakly interacting among each other. This is, in fact, the asymptotic freedom regime. Okay? And they were believed to form a new state of matter, which is called the quark-gluon plasma. So it's a plasma of free quarks and gluons. Now, a few words about the first instance of our universe. Okay? So at a certain point, we had a Big Bang, okay? And then now the time is evolving in this direction, so vertically. And so within the first microsecond from the Big Bang, there were no hadrons formed, and quarks and gluons were in a quark-gluon plasma, okay? So they were behaving as a free object in a plasma. Then at around 1 microsecond from the Big Bang, when the temperature of the universe was already 10 to the 13 Kelvin, the energy density of the universe decreased. Of course, the universe is expanding and cooling in the meanwhile. So the energy density of the universe decreased under the critical value. So we had the opposite phase transition, where now, of course, quarks and gluons hadronize. So they organize inside hadrons, and the first protons and neutrons were created in this age of the universe. Okay. Then, just to go on in this time scale, okay, after 1 second from the Big Bang, okay, so when the temperature of the universe was of the order 10 to the 10 Kelvin, the first nuclear reaction started. This you probably know. This is the primordial nucleosynthesis, and the first light elements were produced in these very early stages, which took just a few minutes. So here, deuterium, tritium, helium, and lithium, possibly also boron, were produced in this stage here. Okay, and then it took something like 400,000 years. Okay, to get the temperature of the universe at a value of 3000 Kelvin, okay, and so low enough to allow the formation of the first atoms. So the nucleus was now capturing an electron and forming atoms, okay? And then starting from this point on, the radiation can now propagate freely. Okay, what about today? So after 14 billion years, so today, we have good expectation that the quark-gluon plasma may still exist in the core or some neutron stars, which are very compact objects, as you probably know. Okay, you know what neutron stars are?
I do.
Ok, avete studiato sicuramente nei corsi di astrofisica.
Ad astrofisica, corso con i rosati.
Perfetto, perfetto. Perfetto, quindi sono stelle di raggio molto piccole, estremamente dense, e nel nucleo di queste stelle si suppone che ci siano le condizioni tali da far sì che quark e gluoni si trovino in questo plasma di quark e gluoni, appunto. Ok, what about now the experimental search for quark-gluon plasma at accelerators? Okay, so in the last decades, the quark-gluon plasma has been reproduced and studied in ultra-relativistic heavy ion collisions. So it is not anymore a collision between protons or electrons, but we are now colliding golden nuclei or lead nuclei, okay, at high energy, so ultra-relativistic. And this has been done mainly at the Brookhaven National Lab in New York and at CERN, okay. So you see, when you collide now two of these heavy nuclei, there are hundreds and hundreds of nucleons, okay, that participate in the collision. And so there is a large volume in which the quark-gluon plasma can be created if the energy density is high enough, okay. Now, these are now the main experiments that have been perpetrated in the last 30 years. So at Brookhaven National Lab with the AGS accelerator in the early 90s, they were colliding a gold nucleus with a center of mass energy of 5 GeV, so rather small energy. At the CERN superproton synchrotron in 1994, there were a series of experiments based on the lead-lead collisions at center of mass energy of 17 GeV. Then again at Brookhaven, but now with a new machine, the RIC, okay, the relativistic heavy ion collider. Starting from the year 2000, they were using now gold collisions with an energy range quite wide, so from 8 up to 200, but actually also now 500 GeV. Okay, and then finally, of course, at CERN, at the Large Hadron Collider, so starting from 2010, now colliding lead-lead nuclei at an energy even larger, of course, the energy of the Large Hadron Collider. So the center of mass energy per nucleon of the order in the range of 2.76 up to 5.5 TeV. So clearly, as soon as you increase, so given the same volume, because you are always talking about a very heavy nuclei, but as soon as you increase the energy, you are also increasing the energy in the volume, so the energy density, okay? And so moving this way, you are enhancing the probability of creating the quark-gluon plasma. So this figure shows you what happened essentially. So suppose you are now colliding two heavy ions at ultra-relativistic energies, okay? Then there is a big volume like this one, okay, where a big number of nucleons are involved. And if the energy density is sufficient enough, then the quarks and the gluons escape from the nucleons. Essentially, the nucleons do not exist anymore. And quark and gluons mix and behave freely in this soup, okay? And this is the QGP phase, okay, which can be essentially studied in terms of hydrodynamics. Then this volume, of course, as soon as time evolves, increases, okay? And it, at the same time, also starts to cool down, okay? So after a certain time, when the energy is below the phase transition threshold, then the free quarks and gluons start now to hadronize, okay? So they form a first gas of hadrons, okay? These hadrons evolve further in time when the volume again is increasing and cooling down. And at a certain point, the final hadrons are emitted, and this is what you observe in your detector. So at the end, you observe, of course, hadrons out of all this process here. Okay. Now, this is just an impressive picture from the HELICE experiment at the Large Hadron Collider. You know that HELICE is the detector, the experiment that is indeed fully or mainly devoted for the study of quark-gluon plasma. Okay. So when you collide lead-lead at these huge energies, you see that you can create thousands and thousands of particles. So each line here is a track of a charged particle produced per each collision. Okay. So of course the performance of this detector must be extraordinarily high in order to track down and identify all these tracks per event. Now, a quick question is whether in our collision we did indeed create quark-gluon plasma or not. How can we know that? Because at the end, we anyway observe hadrons or jet of hadrons, okay? So there are several signatures that have been proposed by theoreticians, okay, that could indicate the formation of the quark-gluon plasma in the initial stages of the collisions, okay? The first of these signature is the enhancement of strangeness, okay? So consider now this picture here, okay, where we have essentially a plasma of quarks and gluons, okay? And the large number of gluons in the plasma leads to an abundant production of strange-anti-strange pairs, you see, via the gluon fusion process, so gluon-gluon that goes into SS bar. And as a consequence, now, of course, when the system expands and cool down, these strange quark will hadronize, and so will form strange baryons or strange mesons, okay, such as the Xi, the omega minus, etc. And hence one expects that the production of strange particles, so essentially of hyperons, increases compared to the case where no QGP is formed, which is, for instance, in proton-proton collision, okay? And these are, in fact, the results. So these are the results from STAR experiment at RIC and from the HELICE experiment at CERN, at the Large Hadron Collider. So what you see here is essentially the increase of production of strange baryons, so of hyperons, as a function of the number of nucleon participating to the collision. Okay, so clearly, the more central is the collision between the two colliding nuclei, the higher is the number of nucleons participating to the collision. So the higher is the multiplicity at the end. Okay, and the higher the multiplicity, the higher is the probability that you form a quark-gluon plasma. Okay, and so you see how the production of these hyperons increases with multiplicity compared to 1, where 1 is the reference that you obtain by colliding proton-proton instead of gold-gold, okay? So here you assume that there is no quark-gluon plasma production because the volume is too small. And so compared to this reference, you see how the production of hyperons increase when you actually collide ultra-relativistic gold-gold you make ultra-relativistic gold-gold collisions. And this is the analogous result from HELICE, of course, at a higher energy. Now we are 2.76 TeV per nucleon and using lead nuclei, but the effect is exactly the same. So there is a clear enhancement of strangeness in this kind of ultra-relativistic collision compared to proton-proton collision, where you don't expect the formation of the quark-gluon plasma. Now, this is not the only signature. Another proposed signature is the suppression of JEPSI production. So the production of JEPSI is expected to be suppressed because the C and C bar quarks, which are produced by the gluon fusion, much like the strange and anti-strange, in this case, they would be separated during the freeze-out by the presence of a multitude of lighter quarks, essentially many up and down quarks, okay? Leading at the end to the production of charmed mesons. So at the end, the two CC bar, okay, that are produced in the gluon fusion get separated, and it is very unlikely that can recombine to form a JEPSI. Okay, it is more likely that they combine with a light quark to form, for instance, a D meson. Okay, and this is also observed experimentally. So you see here are now these results from different experiments at CERN. So here you see essentially the energy density in JeV over Fermi cube. okay? And you see that the results, which are the ratio between the measured and the expected J psi, are essentially close to 1. So you observe exactly what you expect until an energy density of 2.5 here, okay? Then something happened. So here, this is the point where indeed the phase transition occurs. So at this point, the energy density is sufficiently high to create quark-gluon plasma, and then you observe this decrease of the J psi production, which is extremely clear from this plot, okay? And another mechanism, let me say here again that this actually works to, let's say, intermediate energy experiments, okay? So up to RIC, it is still observed, but now when you go at the Alice energies, this is not anymore observed, because now we essentially get, the production of CC bar is so probable that we end up essentially in the same situation of the SS bar. So at the end, in Alice, they even observe some enhancement of the J psi instead of a suppression, okay? So this, of course, depends on the energy. This is a signature working at, let's say, low or intermediate energy. And then there is another effect, which is the jet quenching. Suppose now that you create, so you have two quarks propagating in the plasma, okay? At a certain point, they have to hadronize in the way we have discussed today, okay? And now, depending on where the quarks are created, with respect to the volume of our quark-gluon plasma, they can be very inside this volume, or they can be close to the periphery of the volume, okay? So what happens is that while this quark travels inside this very hot, dense matter, they lose energy, okay? There are energy loss affecting QGP, which are essentially given by this radiation of gluons. So the quark lose energy in this hot matter by radiating gluons, okay? And it loses much more energy if it is inside the volume than if it is created close to the border, okay? So what you observe is an asymmetric jet production. So in this case, you would observe a very large hadron jet. In this case, a very small jet, which is a quench jet, because most of the energy of the quark has been absorbed inside the medium. And this is an example of experimental evidence for this. So here you see essentially the azimuthal angle, and this is the polar angle in terms of the pseudo-rapidity. This we will study next, okay? So this is to give you essentially the eta angle, and this is the phi angle. And you see here now, this is a calorimeter, okay? So this collects the energy of the jets, hadronic calorimeter. And you see that one of such events where you have a very high energetic jet, the leading jet here, this kind here, and a suppressor or subleading jet, which is the quench jet there, okay? There are clearly several others signatures for the quark-gluon plasma, like elliptic flow and others, which we will not discuss here. They are too complicated and technical for this course. So let's now conclude. So what are now the observations of the quark-gluon plasma, how it looks like? So contrary to the original expectation of a gas-type behavior, the present experimental results, mainly from RIC and a Large Hadron Collider, indicate that the quark-gluon plasma behaves like a near-ideal Fermi liquid. That is, essentially, it behaves like a liquid with essentially no viscosity, zero viscosity, or zero internal frictional resistance. And these results are, of course, based on an hydrodynamic interpretation of the QGP variables, okay? Now, this plot here gives you the full QCD phase diagram, okay? So in this corner here, we have the standard matter, in particular when, okay, so here we have the temperature and here we have the baryon density. So at the density 1, we have the standard nuclear matter, okay, which sits here. And this we call essentially the region of hadron gas. Then there is something happen in this border here, which is indeed the phase transition, okay? And this can happen in two directions, either increasing the temperature, okay? And this is what you tend to go when you study very high energy experiments, or by increasing the density. And this is what you observe, for instance, in neutron stars, okay? Or in any infinite possible intermediate scenarios, okay? In any case, you are moving from a phase of hadron gases to a phase of deconfined quarks and gluons. And in particular, there is also expectation for a critical point, okay, where the two phases should coexist. Now, what about experiments? So the RIC and LXC experiment are very high energy experiments, so they move through this direction here. So the transition should appear around in this region here, okay? Because they provide a very high energy density, and this corresponds to very high temperatures, okay? There are also lower energy experiments, also searching for quark-gluon plasma, okay? Which, of course, will access this QGP phase in a different point, on a different region of the phase diagram, okay? What about the early universe? The early universe, the phase transition was acting in the opposite direction, of course. So we are in this corner here with extremely high temperature, extremely high energy density. But as soon as the universe started to expand and cool down, okay, then at a certain point, the conditions were such that quarks and gluons started to confine into hadrons. And so the transition was in this direction here, okay? And then there is a last corner here, which is the color superconductor. This is an extremely high density region where quark pairs are expected to behave like Cooper pairs, you know, which are the basis of the superconduction in the standard superconduction, okay? So essentially, quark pairs would behave as a fermion pair, so like a boson. And so this would allow also boson condensation. And this is an extreme behavior of matter, ok? Va bene, questo è quanto avevo da raccontarvi oggi. E con questo chiudiamo anche il capitolo della QCD. Domande, curiosità, dubbi?
Scusi, avrei una domanda riguardo proprio quest'ultimissimo argomento dei superconduttori di colore, diciamo. Queste appunto coppie di Cooper interagirebbero quindi mediate comunque da gluoni?
Sì, ora non so i dettagli perché non sono un esperto di questo. Il punto è che sì, ma non ne so molto in realtà, non so quasi niente a dire il vero. Quello che succede è che la densità è tale per cui, diciamo, queste coppie di quark di fatto collassano in una coppia di Cooper e si comportano con proprietà bosoniche, quindi possono anche condensare. Quindi quello che succede è che a questo punto il colore, tramite ovviamente gluoni sicuramente, è libero di scorrere come se non avesse resistenza. E se vuoi l'analogo della corrente elettrica o la resistenza elettrica. Okay? Però davvero più di questo non ti so dire davvero.
Va bene, grazie.
Posto.
Va bene, se non ci sono altre domande, dunque fatemi un attimo capire. Eravamo in 3 a ballare l'Alligalli e siamo sempre in 3 a ballare l'Alligalli. Vabbè, pazienza. Vabbè, provate insomma a sentire i vostri colleghi, insomma, a esortarli un po' a seguire. Dopodiché noi, vabbè, ci vedremo quindi settimana prossima, mercoledì. Oggi siete stati voi 3 molto puntuali, quindi vi esorto a continuare ad essere puntuali il mercoledì, così quando cominciamo alle 9 partiamo abbastanza sharp, per evitare poi di sforare l'ora successiva di Pagliara. Settimana prossima invece affronteremo il capitolo successivo, che è quello dello studio della struttura interna del protone o del nucleone in generale. Ok? Va bene. Allora, buon weekend e